Good morning to all of you. Good morning. I was wondering if you all still are asleep from last night. So my name is Sethuraman Panchanathan. People call me Punch. I'm delighted to welcome all of you. So one of the things that I thought I'll take the privilege of talking a little bit about ASU, because you're here and a captive audience. And I'm going to say a few words about ASU and welcome you to Arizona. I know it's the last day of the conference, but yet I wanted to give you a quick snapshot of Arizona State University. So ASU is the largest university in the United States. We have got about 72,000 students on campus, 26,000 of them are online. So it's a very large university. But at the same time, it's also a university that is sort of progressing rapidly in terms of research. So in the last 15 years, our research have quintupled. So in 2002, we were about $100 million of a research enterprise. This year will be about $510 million as a research enterprise. We are the fastest growing research university in the United States. And we're very happy about this testimony that was given by US News and World Report as the most innovative university in the United States for 2 years in a row. And ahead of Stanford, which is number 2, and MIT, which is number 3. And you see that vibrancy, even in downtown, we have a campus which is just north of here. If you walk down, you will see the campus that never existed in 2002 is now very vibrant. The Tempe campus, which used to be called the main campus, has got some very exciting activities there too. So we have spread over the larger metropolitan Phoenix area, 5 academic campuses. We recently acquired the #1 international management school called Thunderbird. And then we have 3 innovation campuses. So we work with the cities, and it is a rapid evolution as an institution. So if you have the time, since you might decide to stay a couple of days more, I welcome you to visit ASU and experience that energy that permeates ASU. So I'm very excited to have all of you in Arizona. And one of the things that we can say safely in Arizona is we will provide a warm welcome. Doesn't matter what time of the year. Sometimes hot, sometimes even hotter welcome. So that's one thing that Mike and I can do, without any, compunctions whatsoever. So welcome again, and I just want to quickly dive into the keynote speaker. I don't want to take any more minutes from his wonderful talk that we're going to hear today. When you talk about somebody like Rico Malvar, he doesn't need introduction to this community at all. And so, but then you still do this because there may be a few students out here who may yet not have read his extensive bio. They may know have read of his papers, read his work, but may not know the fantastic person he is and what a significant accomplishment he has achieved. And so just for that sake, we are going to sort of go through this bio of Rico here. So Rico Malvar is a Microsoft Distinguished Engineer and Chief Scientist for Microsoft Research. He was born and raised in Brazil. Before moving to industry in 1993, he was a professor of electrical engineering at the University of Brasilia, Brazil, and was Vice President of Research and Advanced Technologies at PictureTel from 1993 to 1997. I'm assuming some of you were even born after that. He joined Microsoft in 1997 when he started a signal processing research group which developed new technologies such as new media compression formats used in Windows, Xbox, and Office, microphone array processing technologies used in Windows, tablet PCs, and Xbox Kinect, as well as machine learning technologies for music identification in Windows Media, junk mail filtering and exchange, and others. Thank you, Rico. My filter does work well. The group also developed the first prototype of the roundtable video conferencing device. Rico was a key architect for several media compression formats, such as WMA and HD Photo, JPEG XR, and made key contributions to the popular H.264 used in YouTube, Netflix, digital TV, and many other applications. Rico received his PhD in electrical engineering and computer science from MIT in 1986. His technical interests include multimedia signal compression and enhancement, fast algorithms, multi-rate filter banks, and multi-resolution and wavelet transforms. He has over 160 publications, and just watch this, and over 115 issued patents in those areas. I've seen very few people at that level of patent issues. Fantastic. He received the Young Scientist Award from the Marconi International Fellowship in 1981 and was elected to the Fellow of IEEE in 1997, received the Technical Achievement Award from IEEE Signal Processing Society in 2002, and was elected a member of the US National Academy of Engineering, a huge accomplishment, in 2012. He's also a member of the Brazilian Academy of Sciences and Brazilian National Academy of Engineering. I mean, pretty much you can say that he is everything that you can ever imagine that you want to be. As a budding scientist, I tell you, that is what you look forward to being. And so it's a great honor and a distinct privilege to have Rico deliver to us the talk today on media information processing for computing systems. Rico?
Thank you very much. Looks like the audio is working all right. Thank you for the introduction. I think you inferred by now that I'm not 25, but just a little older than that. Okay, I appreciate your waking up to this. And I warned Michael when he invited me to present this keynote that I know this is an image processing conference. I do a lot of work on image processing. But you've been, after 2 days of lots of image processing, what if I talk about some other stuff? I hope you appreciate that. But I'll have a few nuggets of image and video processing as well. So let's go. Okay. Oops. Oh, it works better if I turn it on. All right. So let me tell you a little bit about the contents. So I want to talk to you about some advances in computing, in particular, things related to media information process. By media, I mean speech and audio, and of course, images and video as well. Probably things that you will like. You may have seen some of those things here in some other places, but you probably haven't seen all of that I'm going to show you in a single place. So this represents the work of a lot of people, mostly at Microsoft, because I feel more comfortable talking about things we've done. So it's not about the state of the art. It's about giving you a glimpse of what Microsoft Research has done in media information processing. So, but to give you some context, I know many of you already know about Microsoft Research, but some may not. So I'll start a little bit with some bits about Microsoft Research, who we are. We refer to ourselves as MSR. And then I'll show you some interesting new technologies for media processing that actually lead to new experiences, some of them significantly new and I believe significantly important. All right, okay, let's go for that. So let me tell you a bit about Microsoft Research. So my bosses get happy that I came here and I did a little bit of advertisement, but it will be just a little. So we were founded in 1991, so as you can see, we just turned 25, so we're not that young anymore. We just became adults. We have core labs all over the world for a simple reason. Smart people are everywhere in the world, and it's easier to be everywhere than to think that everybody's going to come to the US. We have these advanced technology labs where we actually try to do more applied research, where we pick up specific scenarios and then develop technologies to address those. It's interesting that even though those labs, for example, we have those labs in Germany, in Egypt, Israel, and Brazil, and even though we are motivated by some scenarios that are they surface locally, at the end, all the technologies we develop, we find that they have application globally. So the world is flat, and this diversity of locations also helps with diversity of ideas, right? Because good, smart people are everywhere, and when they are in different societies with different ideas in mind, that just generate new ideas for new technologies, and we can try to tap on that. We try to hire very good people, so we have over 12 members of the National Academy of Engineering, many fellows of the IEEE and ACM, and we won many awards, including the very prestigious Turing Award from ACM, Draper Prizes. We even won Oscars, not for acting or directing, but for technical contributions to the movie industry. We publish most of what we do, I would say at least 95% of the work we do gets published in a way or another, so we're a very open organization. Thousands of papers, hundreds of patents, lots of tech transfers. One thing we like to say is that not every project in research sees the light of day. In fact, only a very small fraction, because otherwise it wouldn't be research. Most of research actually fails. Some of it, though, works and gives you a competitive advantage. So what we like to say is that every product of Microsoft, really, from Windows to Office to Bing to Xbox, Azure, everything, Cortana, has significant contributions from Microsoft Research that made a difference. So the idea is try to find the right balance between push the state of the art and actually bring those contributions to be real. And people get excited because in a company like Microsoft, if you do ship something, you have an opportunity to have hundreds of millions of people or even billions of people using your technology. That is really motivating. Okay, so more bits. Since we have many students in the audience, I did want to mention this because it is important. Because we have many programs with academia. Actually, a sizable portion of our budget for research, which I won't tell you how much it is, but I mentioned before we're about 1,000 people, so you can have an idea what's the budget necessary to run a 1,000-people organization. But a good fraction of it, actually, we spend in programs with academia. So we hire about 1,000 interns every year. We have postdocs, fellowships for students, fellowships for faculty. And we actually share with academia. I'm just showing a couple of examples like code contracts, things that help you write much more efficient codes, which today they are in Visual Studio, so you can use those technologies so your code is less likely to have bugs to begin with because it was designed in that way. But those tools, actually, we make them available for free for academic use years before they get to show into the product. So academia really has first dibs in many of those technologies, especially in software engineering. And we do that first because it's a good way to help academia, and we care about that. Second, because the students are so bright, they find all kinds of bugs, they let us know, and we try to improve the product. And of course, hopefully, if you really like that product, then once you graduate, become an engineer professional, hopefully you will continue to use that product. So everybody wins. We have a program called Azure for Research, where we get proposals, and you can propose the school project, and if you get selected, you actually get free time in research in Azure, so you can get significantly processing power. Actually, I will show at the end what significant processing power can mean, right? And we have the Connect SDK, so you can easily download the SDK. You saw about Connect yesterday. You can develop all kinds of interesting things, and the SDK is free and all kinds of capabilities. We just recently introduced the cognitive services, which again, you can try it out for essentially free, and it will only cost you once you actually develop big applications with it, but it brings all kinds of machine learning APIs. For example, speech APIs, natural language APIs. You can, for example, upload a piece of text and ask back if that text is positive, negative, if that is a joke. All kinds of metadata about the text. You can upload some piece of speech and get back the text corresponding with the highest possible quality speech recognition. So the ability for you guys developing applications with speech, natural language, and all of that, and image recognition as well. You upload a picture, get back a description of the picture. You can put all of those capabilities in your app by just calling the cloud APIs. So I put some links over there. They are easy to remember. Check them out. I think you'll find them very interesting. Okay, I like to say in my presentations that we're going through a golden era for research. And to this audience, I don't think I need to reinforce this point that much. As you can see, we have this inflection point in computing capabilities. Moore's law is slowing down. There's only so much we can double the number of transistors in the same chunk of silicon until the transistor gets too small, right? And the too small is not really a limitation of the basic physics that will make the transistor not work. It's much more about the cost of a factory to make that. If you keep going to Moore's law 5 years down the road, exactly as it is, you would end up with a factory that might cost $20 billion. right? If you want to make the super powerful chips, who's going to invest $20 billion in one factory? So we're finding other alternatives, and you're very much aware of that. For example, yesterday from NVIDIA, you heard about advancements in GPU where you can have hundreds of cores, thousands of cores to help the processing. So you parallelize the number of cores instead of assuming that each core is going to have smaller and smaller transistors. And I'll show you how you can go a few orders of magnitude beyond that a little later. So that's to make sure you're awake. So another thing is computers that can see, hear, and understand. For example, one thing we learned very much about Connect. You heard about Alex Kipman. He was really a visionary when he decided to push for Connect. We worked very closely with him when he approached us and said, oh, I want to do this thing that is going to just detect the gestures and build skeleton models. And you heard from Jamie Schotten yesterday how you do that. And of course, as Jamie said, first time Alex asked the question, he said, no, can't do it. And then he said, oh, okay. But Alex didn't want to hear no, kept insisting. At some point, he said, well, maybe. And then it actually did work. And we learned a very interesting thing. This will sound like a joke, but it isn't. When we did the Connect, the challenge was make a system that you can control the computer, in particular a video game, without touching anything. There's no controller, there's no button to press. You can only make gestures and speak. Can we make that work? And by now, it's well known. We shipped the first version almost 6 years ago. You all know that's possible. But that brought to us a very important concept, and that's not a joke, which is the following statement. When there is no button to be pressed, you cannot press the wrong button. Did you get that? Right? So have you ever heard a friend or a family member that comes to you and say, oh, this remote controller for the TV, so many buttons. It turns out that when you have a computing system or a TV or a multimedia system, when you have a remote control or a keyboard, if a person presses the buttons and something wrong happens, they think they pressed the wrong button and they feel bad about it. If you're controlling the computer by voice or by gestures and the computer does the wrong thing, and you say, I spoke my language, which is gestures or voice. I know how to speak my language, so if you didn't get it, it's your problem. That makes a huge difference on how people approach computing. So this idea of computers that can see, hear, and understand is really incredible. And I don't need to tell you that. I mean, today you have Cortana, Siri interfaces where you just talk to your phone and you get the information. The phone can relay back to you the information also in voice, because you may not be looking at the screen at the time. Makes a huge difference, because now the interaction is in human language, not in the computer language, right? And recent advances in machine learning, I'm pretty sure there's several of you who are experts in machine learning, so I don't need to tell you much. Natural language processing, signal processing, advances in sensors. The touch panels are better, the microphones are better. There are so many things that get together and we can actually deliver those things. And cloud computing growing very rapidly. It's not just, okay, pick up the same computer that you have on your desk, put a bunch of them in the cloud, let's say 1 million, and then now you have a powerful thing. That's not enough, and I'll show you later why that's not enough. And also another thing I like to talk to you about is that I don't need to tell to this audience here, but just to make the point clear, research is certainly a long game, right? Look at you guys, especially students, take you several years until you get your PhD, and then you get your PhD, and then you realize, I know a lot about this much. And you say, oops, there's a lot more to be done to build real things. And then you start your career. And even when we start projects, for example, we talked about Connect, and you can see in the middle video there, in the middle left, the same body segmentation technology that Jamie presented yesterday. In fact, those are his slides. And that was in the first version of Connect in 2010. A few years later, we introduced Xbox One, and we had a new version of Connect. You can see that the length of the Connect is about the same, and is basically defined by the distance of the microphones, because it has 4 microphones. And I'm just showing on the top left our first prototype microphone array, which was made out of erector sets and other things, which is pretty bad. But look, from 98 to 2004 until we made our first USB connected microphone array with 4 microphones. And then 6 years later, that same technology that we've been developing for years. So when Alex came back to us and said, can we do the Connect? And by the way, can we do it in less than 2 years? We ultimately said yes, because we had over 10 years of computer vision research that allowed that kind of body modeling for skeletal models. And we also had more than 10 years of audio signal processing to be able to deliver microphone array beamforming, so we can zoom into the person speaking, even if you have more than one person in front of the sensor, and also the computer vision. And you can see there, let me go back to this slide a little bit, just to restart the restart the bottom animation. Let's see. Apologize for that. Okay, the bottom one is not running. Sorry, the goal of the bottom one is to show you, let's see if I can make it start from here. No, apparently it didn't get the link. Apologize for that, but it was just to show you that the skeletal models that we started shipping in 2010, they got a lot better in 2013, so that when you're developing a game on the APIs, not only you know the body positions, but those colors, they have additional meaning. For example, if you make a jump as you're dancing or things like that, we can actually give you in an API the pressure, an estimate of the pressure by which your leg is touching the ground. Or if you hit your arms, you can always, from the API, say how strong that contact was. So you can get additional, more sophisticated models because of the significant larger computer power from the new Kinect compared to the old one. And in the previous slide, the idea of gestures, the video that I put in there, let me restart that one. Remember yesterday, Jamie talked about gesture estimation with Kinect sensors, and this show works they published late last year, where you can see that even the hand gestures can be very well detected. In fact, with a combination of computer vision to detect the fingers and some prior models that it is a hand, and you try to adjust via computer graphics model, a mesh model of your hand and fingers, you can actually get pretty good estimate. There's a little bit of noise, but by now, there's probably already something running that has less noise and it's more smooth. And if I ask you, what can you do with that technology? I bet you can imagine many applications, right? Because now I'm at a distance from a screen and I can do very sophisticated gestures that the computer understands. So I can now control a big screen that I don't need to touch. I can control it from a distance. It could be a big screen on a panel. I can be a doctor operating in a patient, and with my hands, still with the gloves in my hands, I can control a computing system without having to actually touch it. Because if I did, I would probably have to replace my gloves and take a lot of time. So let's keep going. For example, on the Kinect, one of the problems we had to solve was multi-channel echo cancellation, which until about 20 years ago was deemed unsolvable. And then we just changed the model a little bit. On the left, you see a little bit, if you try to do 2 independent adaptive filters, it actually doesn't work very well. But if you change the model by breaking the filters into 1 common filter and 2 independent ones, and you use some algorithms to estimate them differently, then you can actually get convergence even on a multi-channel. And I'll give you an idea what echo cancellation, for those of you who may not have seen what it means. The main problem is you're playing a game with Kinect and your phone rings and you want to stop the game. So how do you stop the game? You say, Kinect, stop. But there's a lot of noise going on, the noise from the game itself. How can the system hear your voice without that noise playing? Because you know the voice, the sound you're playing, you can subtract out. But before you subtract, you have to estimate the effect of the loudspeakers, the acoustic of the room, in the noise that gets back into the microphone. So let me show you an example.
Xbox, sign out. Xbox, switch profile.
Did you hear the commands that he was saying? It was very faint, but after you run the echo cancellation,
Xbox, sign out. Xbox switch profile.
So you can hear Xbox switch profile, and all that noise from the game goes away. There's a little bit of distortion in the voice, but we tuned in such a way that that distortion doesn't hurt the speech recognition, so it still works very well, right? Okay, so let me talk a little bit about an interesting application of different technologies. We have been doing speech recognition for a long time because that was very important for Windows. In fact, one of the first research groups was speech recognition because then by putting speech on the operating system, you can actually control a computer using your voice because your hands may not be available for some reason or you just prefer to use the voice, right? And Windows actually can be controlled by voice. And we also, for about 10 years now, we've been shipping in Bing, you've seen, text translation. You can open a web page in one language, ask it to be translated, or if you just have a piece of text that you want to translate, you can put it in a window and it gets translated to another language. And in fact, what if we put those together? So we had a challenge. What if we translate not text to text, but speech to speech? So we started with that challenge. Can you translate speech to speech? And later thinking about how to put that in Skype. But let me go back, for example. Imagine you have a person, in this case Rick Rashid, who just retired and used to be the head of Microsoft Research. He was the founder of Microsoft Research. So he's speaking in English. You go through language translation, and then you do, for example, in Chinese synthesis. And in fact, that language pair was the first one we looked into because there's a lot of people who are interested in translating English to Chinese, right? So it sounds easy, doesn't it? If I ask you, how can I translate speech to speech? You might say, aha, pick up a speech recognizer, you pick up the voice, convert to text. Go to a text translation engine, convert to text in the other language, go to a speech synthesizer, and you speak out the other language. That's fine, except that it doesn't work very well, and it has latency. So I didn't want to put too many equations, but that's the last one, I think. One thing we learned is that you don't want to actually cascade a speech recognizer with a text translation. You actually want to put them together. For example, for many of you in who understand speech recognition, usually the output is just the best out of a list of n possible outputs. It's better to actually send the list and create a trellis to the translation because the second best in the list might actually be a much more common phrase, and given the context is more likely to be that one. So it's better to make a joint decision between recognition and translation than to do those things independently. So we learned about that, we implemented that, we made a system that does that in a sequential form, so to reduce the processing delay, as you're speaking, we're spitting out the translated speech. You don't need to finish a sentence because we want the translation to be fast. And these capabilities are actually available as cloud APIs that you can go in and develop applications that use this kind of technology. I think I don't need to tell you much about using deep neural networks. There was a lot of this conference about deep neural networks. If you go to ICASP or if you go to the speech processing conferences, you will see, or computer vision, you see a lot of deep neural networks. And you know that by putting big enough networks, you can improve significantly the quality of speech recognition. This plot is very interesting, which shows that sometimes when you're working, like for example, I work a lot in data compression. And then we improve compression a little bit, and then 2 days ago I come to ICIP and somebody brings a paper on image compression. I'm now 20% better, and I was like, what? But it can happen. So sometimes you have, for example, speech recognition between the years 2000 and 2009, very little progress for about, actually a little more than 10 years. But people didn't give up. And about that time, in a combination of work by Microsoft and other folks, we started adding deep neural nets to speech recognition. So the error rate, which was above 20%, suddenly goes below 10. And you say, whoa, not only that is cool because you are able to reduce it quite a bit, but you could say that for many practical applications, above 10% error rate is really hard to produce a good experience. Below 10%, you enable a lot of experiences. For example, translation. If I want to do speech translation the speech recognition part should have an error rate below 10%. Otherwise, the overall experience is not going to be so good, and you're going to have lots of errors in the output. So up to maybe, it's been about 6-7 years that we're being able to get speech recognition that is so good that you can actually translate speech, right? And another thing that is interesting is that you can actually convert speech from a timbre of one person to a timbre of another person. Why do I care about that? Imagine back to the speech translation scenario. You're speaking in a language, the computing system is going to translate your voice to the other language. But if the final element of the system was a speech synthesizer, then the voice that comes out is the voice of the synthesizer. It's not your voice. Wouldn't it be nice if it were your voice? So we ask the question, if I have speech synthesized by a reference speaker, can I pick up the parameters of another person's voice and now produce an output in that person's timbre? So let me show you an example of that. So in this case, in the top is as a reference speech, a person speaking in Chinese, and then we pick up the same sentence and do a spectral mapping to the tone of the other person. The goal is that you're going to end up with the same sentence, with the same intonation, all the same characteristics, except that it sounds like another person. Even in this case, if you start with a female speech and then convert to a male voice. Let me show you an example.
把不可能变为可行的语音翻译计划。
So that was the original, now after the conversion.
把不可能变为可行的语音翻译计划。
So as you can see, the speech is very smooth, it's very clear, but now it sounds like a different person. So we can actually borrow this technology and have a speech-to-speech conversion that will sound like you. We're not quite yet shipping that, because I want to give you some nuggets of things that are not out there yet. But it's going to get there, and hopefully it will be also available in cognitive services, and again, will allow you to create some interesting new apps and experiences. I'll show you an example. First time we finished an end-to-end speech translation system, which was actually running on a very powerful computer using deep neural nets. Now actually we're using deep neural nets both for recognition and for synthesis. At that time, we were using deep neural nets just for recognition and more traditional methods for synthesis. And this is the first time we actually demonstrated. We went to Tianjin in a presentation to a very large audience. And at some point, when Rick was presented, we turned on, as you can see on the top left, captions. So as he was speaking, it was automatically being captioned. You've seen that before, right, in closed caption TV, for example, except that it was being done automatically, not by a person. And then automatically translated to Chinese on the second screen. And then after a little while, we actually added a little delay so you could feel the effect. His own voice would come up in Chinese. Let me show you. Just a few seconds of that.
In a few years, that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
Personally, I believe this is going to lead to a better world.
我个人认为这将导致更好的世界。
I hope you enjoy the rest of the presentations today.
希望今天你喜欢其他的讲座。
Thank you.
谢谢。
That was funny. In the simple sentence, which was thank you, that should be translated to 谢谢, the system somehow took a little longer to do that. And, that was a very first demo. And we were there behind the screen going with a big red button just in case something didn't work. But this was the very first version. And I did pick up the audio with the clapping for the audience, just to show you that first time you show something like that, people really got, whoa, can you actually do that? Of course, is the quality of that system as good as if you had a human translator, right? Not quite, but we're getting there. The advantage is that this system doesn't get tired. You could use it for a long time. But then what do you think we would do with that? Once we show we have this capacity, where do you think we could use this technology? In Skype. Because Skype is already a system. I bet all of you know what Skype is. Many of you have used Skype. And Skype did a very good thing for us. It took away the barrier of distance. Because when we use the old telephone to make a call to India or to China or to a place far away, it costs a lot of money. You go to Skype, that call is free. Whoa, now you talk to your relatives much more. Except that when you talk to your friends and relatives, maybe you're here in the US, you speak English very well, they don't. Or maybe it's your kid who was born in the US who does not speak well the native language. So how do you get the kid to talk to grandpa and to grandma, right? So what if we then put this voice translation technology in Skype? So let me give you first an example of the experience you can have with live speech translation.
Hi, can you guess where I live?
¿Te encuentras en América del Norte?
Yes. Do you live in central Mexico?
Sí. ¿Te encuentras en Estados Unidos de América?
Yes. Do you live in a capital city?
Sí. ¿Estás cerca de Seattle?
You're very close to Seattle. Are you in Mexico City?
Sí. ¿Estás en Tacoma?
Yes. Very good guess.
Gracias.
Thank you.
Now you can see the whole
Do
system.
you like living in Mexico City?
¿Te gusta vivir en la Ciudad de México?
Aquí está muy lindo.
Here is very nice.
What do you do for fun?
¿Qué haces para divertirte?
Voy a las playas de México.
I'm going to the beaches of Mexico.
I like to swim.
Me gusta nadar.
A mí también.
Me too.
Where in the world do you wish to travel?
¿A dónde en el mundo te gustaría viajar?
A Rusia.
To Russia.
¿Y tú?
And you?
Everywhere.
Sería increíble algún día verte en México.
It would be amazing to see you someday in Mexico.
I would really like to visit you sometime.
Me gustaría mucho visitarte algún día.
A mí también.
Me too.
So with that, we took away the barrier of distance. Now we took away the barrier of language. And in fact, this is now, they were using those school kids, one in the US, one school in the US, one school in Mexico. They had no instructions. We just showed them the app. Let's make a call. And you saw that you had the voices transcribed in the messaging windows and also spoken out in their respective languages. And they were able to just carry on the conversation. That's why you saw some of the kids were surprised, because they had no instructions, but they immediately saw what was happening. And as you saw, they had fun. And I just want to show to you, in case you use Skype, so when you pick up, this is the regular Skype desktop windows that you've probably seen, and when you pick up one of your contacts, on the top right, besides the settings, there's this little icon of a world. If you click on that, you can choose which language the other person speaks. And if you choose one language for you and a different language for that person, the translation system kicks in. The voice translation system kicks in. And it's very fast. It's actually faster than a human translator, with the accuracy that is approaching a human translator, so the quality is really high. To give you an idea, I use that technology every week because I have calls, not with a person that doesn't speak English, but I have a call every week with one of my colleagues. She's in a building far away from mine, so instead of driving to her building, we just make a Skype call, except that she's deaf. Now think about it. How does a deaf person take a Skype call? Now you saw how? Because I select in the language English to English, but then it will be translated with the captions. So she can read lips up to a certain point, so she can see me, and then she can read the captions. The advantage of that experience is that she can look at me and not look at a person doing sign translation, for example, sign language translation. So you don't have the issue of sign language being another language, so some of the meeting may lose. Also, she can look at me the whole time. So it was we didn't design for that, but we realized, oh, it can also be used in that application. So it turns out that a fair number, because we monitor the system, a fair number of the translated Skype calls are actually between the same languages. And we imagine must be a scenario like that, where you have a deaf person, or for some other reason, a person who sees the value of having the voice caption, because maybe the person has some accents and they just feel more comfortable having the captions. Right? So I was talking a little bit about the cloud and how powerful is the cloud. I saw in many of the papers that I've seen in the conference, which I must say, this ICIP is really great. It's been a few years that I haven't been to ICIP, and I saw so many good papers. I was like, whoa, I have to come back every year now. And I saw in some of the papers, including data compression and others, some concerns about the complexity of algorithms, where you'd say, well, for example, I can improve compression by 20%, which is very significant, but it will cost me 3 times or 5 times more processing. To which I would say to you, 5 times is nothing, right? So if you invent a new algorithm that is 1,000 times more complicated, go for it, because I can give you much more than 1,000 times more processing. Right? So let me talk you a little bit. When you think Microsoft, it's a software company. Not really. We're also now a cloud services company, which means we build our own computers to the cloud. We can build our own computers. We don't have to take a standard computer from a computer manufacturer with the standard blades that go into the racks of a data center and use that. We can design our own. So in fact, we did that. That board that shows that is called a catapult board. It's about this big. Is just enough to fit into a vacant space on a traditional high-performance blade, so we can add that. So we can pick up a big blade like this and add 4 of those boards, and then now you have a much more powerful machine. So we call this the Catapult project in partnership with Altera Semiconductors, and it's basically programming algorithms to hardware. I was mentioning before, as you saw from the talk from NVIDIA yesterday, if you put GPUs, you can put a lot of cores. Back to the CPUs. The CPUs of your computing system can have 4 cores, 8 cores, 16 cores, maybe up to 64 cores. It will cost you a lot of money, but you can put a lot. As you go to GPU, my little computer here has 500 cores in the GPU. If you get a really powerful GPU, you can have 2,000 cores, 4,000 cores in the GPU. If I go to FPGA, I can have 100,000 cores, 100,000, except that those cores are going to be much more basic, and they can do only very basic calculations. What is that good for example? Deep neural networks. Each little neuron unit, it's very simple calculation. Add a bunch of things, go through some nonlinearity, and poof, that's the output. And you can do 100,000 of those in parallel. So you can actually, depending on what you're doing, deep neural networks is an example. Decision trees, SVMs, there's many machine learning things that you can program in FPGA. It's more complicated, but now you're programming down to silicon, to programmable silicon. And these processors, you can actually reload the code in about 100 milliseconds. So you can solve a problem, reload new code, solve another one. Gone the days, for those of you who are about as young as I, FPGAs were complicated to program. That's past. You program them on the fly, and you can just load the next batch of work. And you can actually improve on the most important metric, which is how much computation you get out of the system, given how much energy you put in. You may not realize, but the cloud, as we know it, Microsoft, Google, Amazon, everybody, uses a lot of electricity. About 2% of all the electricity produced in the United States goes to the cloud. It is a big deal. you can see companies like like Microsoft, our electricity bill at the end of each month is gigantic. So that number I mentioned, how many tera-ops I get out for every kilowatt of energy going in, it is the main metric. And we can improve that metric sometimes by a factor of 50, which is huge, huge. And you will see things like data centers being built close to hydroelectric power plants because now you can get cheaper electricity, right? This project just finished the first version last year, and since then, we've been putting that in the Azure clouds. Now we have over 100,000 servers in Bing and Azure running that technology. And I'll give you an interesting possible application of that technology. Suppose you want to program in it a very sophisticated deep neural network-based translation system to translate text. So suppose I pick up War and Peace and try to translate, let's say, from English to German or to Spanish. I can actually do that in a few seconds just using one of those blades. Now, what if I pick up all of those servers? And just for fun, we actually didn't do that. But if we did that, if we put them all together and we say, let's translate something really big and see how fast we can do it, we actually did the following thing. We did an estimate, and we picked up all of Wikipedia. So all of Wikipedia, it's about 5 million articles, 3 billion words. Pick the most sophisticated text translation system we have with deep neural networks and all of that, and turn up that dial. We actually demonstrated that 2 days ago at the Microsoft Ignite conference, so this is a very fresh result. And actually, we can, if we were to put all those 100 computers together and divide the information among all of them, so not counting the time to bring the data into the computers, just the processing time, how fast could they translate all of Wikipedia? The answer is 100 milliseconds. So think about it. So the comparison that Doug Berger, the distinguished engineer who headed this project, said is, wow, if you blink up to think about that, your blinking takes 0.2 seconds. So in the half the time that you blink, the cloud could translate all of Wikipedia from one language to another with the highest quality possible translation, right? How much computing that is? You saw yesterday that you can have boxes that will give you 10 teraflops or maybe 100 teraflops or even more. All that power together is actually equivalent to about 1 exaflop, which is 1 billion teraflops. So compare a box with 100 teraflops and now think of 1 billion teraflops. So if you look into supercomputing literature, this is probably 10 times more than the most powerful supercomputer that exists in the world. So it's 10 times more. And this is one cloud, just the Microsoft cloud. That shows you how fast cloud is getting and how sophisticated things can be. So when you're worrying back again to the 5x, 10x on your algorithms, don't worry. The cloud will be able to do a lot for you, right? So since this is an image processing conference, I want to close and maybe even leave time for a few questions with a couple of things that actually relates to image processing. Now, come back. I was flying around in other areas. Now, let me come back a little bit to image processing and show you a couple of things. This is, again, a work done by Jamie Schotten and some of the collaborators they published last year. But just to give you an idea that if you use directional filters for applications such as denoising, you can actually improve the capacity of the noising quite a bit without adding artifacts. So just to give you an example of this thing they call filter forests. The complexity is high, but I hope you agree with me now that high complexity is a relative term. So this is an example where you see the original image is on the left with added noise is the second one, and then a bunch of other. Bilateral filter is a very popular filter and what you could get with filter forests. So let's convert this to video so you can see better. This is from their paper. So you can see you still have a few artifacts on the right, but you have much sharper because of the directional filters based on machine learning. So it's just an example, and I've seen similar examples here in the conference. So this is more or less on par with the state of the art, which shows you that by using machine learning, you can actually tune up the filtering so that you can filter more without blurring the image, because you now have directional filters that will preserve edges and other aspects of the image, right? And I just want to close back yesterday again on the afternoon panel. There were some conversations of virtual reality and multi-viewpoint video. And I remember being in a session about data compression and whether we're done with data compression, if there's more things to do. I'll show you some example of work here where actually creates a new kind of images. You have a new kind of video in this case, where you will have video that has been captured not by one camera, not by two cameras, but maybe 100 cameras or more. How do you encode and transmit that information, right? Of course, these cameras, they are looking at the same scene. There's going to be lots of correlation, so there's lots that can be done. And in particular, if you want to compress more, you want to actually put graphic models of the content and superimpose video and images to those graphic models, and you encode the combination. You can actually stream that information. And I'll show you a video a little bit. So this lab setup, I think Gary Sullivan on the panel showed that picture, is an example of a studio where you have, let's say, a person, the scene in the center, and you have an array of cameras. You can have 30 cameras, 60 cameras, 100 cameras, and now the cameras are looking into the scene. You're probably familiar with a bunch of VR cameras that are in the market that do the opposite. You have the camera and they look out. It's much more for capturing 360 video. So back to here, the model is not to capture 360 video. The model is to capture around, have the cameras around the scene. So as you have the signals from all the cameras, at rendering time, you can now navigate for any different viewpoint. So let me show you an example of that.
In this video, we present our system to create high-quality...
Oops. Let me stop a little bit. You will see that the video will rotate. That rotation is not a camera rotating. The cameras are fixed. That rotation is at render time. I can choose my viewpoint, and it's synthesized in real time by the client. Oops. Sorry for that. Let me go back.
In this video, we present our system to create high-quality, free viewpoint video that can be compressed to bandwidth suitable for consumer applications. This example is a traditional Maori haka performance. We start by capturing performances with 106 synchronized RGB and infrared cameras on a calibrated green screen stage. We subtract the background to compute silhouettes, then schedule the data for processing. The first step generates a 3D point cloud starting with stereo depth maps from RGB and IR pairs. Points from these depth maps are merged and refined locally. Then the cloud is refined globally using a multi-view stereo algorithm. This result has over 2.7 million points with normals per frame. We're viewing tens of thousands of points in this scene. The next stage creates a watertight mesh per frame. We modify screen Poisson surface reconstruction to produce meshes constrained by the silhouettes. These meshes typically have topological artifacts and spurious components. To clean them up, we apply topological denoising and island removal. This result has over 1 million triangles per frame. Next, we determine which areas contain perceptually important details such as hands or faces. We preserve the quality of geometry and texture in these areas when we decimate the mesh to its target density. This example is reduced to 20,000 triangles per frame. We then establish temporal coherence by choosing mesh keyframes and deforming them to fit ranges of the performance. This coherence is critical for compressing mesh motion and textures. This example was split into 4 subsequences. The final step is to unwrap the meshes, generate a texture atlas, then compress and encode the data in a single streamable MPEG file at our target bitrate. This example is running at 12 megabits per second. Let's take a look at some example captures from our system.
So as you can see, you get a very high fidelity reconstruction. And just to give you an idea, I don't know if you noticed during the description that all the geometric model plus the textures were all compressed together at about 12 megabits per second. If you recall, suppose you're watching, let's say, a Netflix video at 4K resolution. That's probably encoded between 6 and 10. So with almost the same rate, maybe a little bit more than what it takes to encode 4K video. This is high definition. This is not 4K. This is HD. But it's HD where you can choose the viewpoint, right? And this is initial results. This is not a full system end-to-end, but it shows you the kind of technology you can have. And I doubt our compression system is necessarily the best. This is new kinds of data. There's a ton of work that can be done to encode these new kinds of things. So when just going back, being a data compression person, if you think compression is that dead, think again. First, because there's new kinds of data. Second, because of all the computing power that you can afford to put in. So I would like to close here, and I hope I convinced you, first, that computing is good, and you need a lot of it to do media processing, that those technologies can lead to really new experience to the benefit of our interaction with computer systems and even with each other. And that thanks to the cloud, we can do a lot of processing. It opens up a lot of what we can do. And I hope you'll be inspired by some of those scenarios and drive to find new solutions to those things. Thank you again. Thank you, Panch. Thank you.
That was a fantastic presentation, Rico. So we have time, maybe we have past time, but we will entertain maybe 2 questions. How about that? Any questions from the audience? Yes?
I think there's one here.
So you did a great example on Skype where you actually communicated with a deaf person. How would they communicate back to you? Is there any research being done so they can sign or somehow communicate back to you in real time?
That's a good question.
The question is, how can you communicate back, how a deaf person can communicate back their questions, right?
Right,
yeah.
Exactly. In my case, the example I mentioned, I'm lucky because the person with whom I use the system, she can actually speak very well with very little distortion. So I can easily understand her speaking. That's not always the case. Sometimes the person cannot speak very well. So one possibility is to actually have a speech recognition system that is adapted to potential distortions that you may have when you speak, or for example, use sign language recognition. That is an area of research. We actually have some research in this area. It's very difficult because sign language is not just about the signs. It's about facial emotions. But now that we have some work in the area, and I saw many of you are working on emotion recognition, maybe by putting gesture detection and emotion recognition, we should be able to recognize sign language as well. Good question. Thank you.
One last question.
I think there is a question over there.
Hi, thank you very much for your great talk. And then
Thank you.
the last, the 3D multi-view point was very surprising. And then I wonder how did you deal with, how you dealt with the occlusion? If you, well, do you understand my question?
You mean on the very last video?
Yeah.
Yeah, actually, what this system doesn't show is that sometimes you have a little bit of occlusion, and then those mesh models, they have holes in them, which means that you have to actually synthesize and fake a little bit the information that may be occluded from a camera. But in this particular case, because we have over 100 cameras around, that problem was much less, because what is being occluded by a camera, maybe some other camera has at least a partial view, so you can do a more informed interpolation. But if you have many fewer cameras, then that problem really is a big one. It's actually a good area of research. How can you achieve that quality with many fewer cameras, right? Otherwise, occlusion will be a problem. Yeah.
Thank you very much.
Thank you. I'm going to take the prerogative of introducing the keynote speaker to ask the last question. So, Rico, in these kinds of things, clearly, you need social scientists, humanists, social behavioral folks, and so on involved. Right. So how much of Microsoft research has such people?
Oh, we have entire groups of just folks with that background.
I want people to hear that.
Yeah,
so, because oftentimes the thought is that it is all about...
That's a very good, thank you, Panch. That's a very good question. We have lots of people with PhDs in psychology, in sociology. Sociology is an area that is changing a lot because of computer science. There's whole theses and studies on how do social networks affect how people communicate, and how society is influenced back by the existence of social networks. And because when you build those networks, you have so much data about how people react, that is very, this connects with sociology very well. I'll give you an idea. An experiment we did, if you don't mind, just a minute. An experiment we did in our lab in Beijing. Suppose we monitor you, how you use your social networks. And suppose you allow me to do that, you give me permission to monitor, and I monitor, and I just look at one thing. You're watching the posts and you're pressing like and don't like. And I just see what is that you liked and what is that you didn't like. Suppose I have only that metric from you. With that metric, I can predict your gender with probably 90% precision. I can predict your sexual preference with about 80% precision, and political views, all kinds of things, just by checking your likes, not asking you any question or not actually reading anything that you post, just by looking at your likes. So this is somewhat scary, but it shows, back to your point, how sociology and computing are interacting in very new ways.
Thank you very much again, Rico. Let's give a big round of applause for a fantastic...
Thank you, folks. Thank you. Oh, thank you very much.
A small token of appreciation.
Oh, there's a...
Yep, there's one more.
Oh, sorry. Thank you very much. Oh,
this
super.
is something from Arizona.
Oh.
The Hurt Museum, apparently. So.
Oh, very nice.
And small enough that you can put it in your hand luggage.
All right.
Yeah, otherwise it might break.
Thank you. Thank you all. This is very nice. Thank you, Dennis. Thank you.